So first of all, we have basically a very similar environment available that we are using when we are working with a hardware board. So on the left hand side you see we are attaching a third-party software debugger to the virtual prototype. But in this case we are not doing that through a JTAG cable. The connection is pure virtual and realized through a debug server that is sitting in the virtual prototype and also responsible for synchronizing multiple embedded software debuggers that you can attach to different CPUs or microcontrollers or DSPs in the virtual prototype. Next to the debugging aspect, the user can interact with the virtual prototype using so-called virtual and real-world I/O. So again, instead of attaching a serial cable to the hardware board and launching a terminal application on the host, a virtual connection is established here between the different external applications and the virtual prototype. So I can connect a UART terminal application to my virtual UART, as well as a VGA console, frame buffer console with keyboard mouse interfaces, 2x keyboard and mouse interface peripherals. And with that I can also realize entire prototypes of new devices such as handsets. We see one here running Android Lollipop. So I would like to quickly demonstrate what I've just described in the slide. So in this window we see the terminal which is connected to the UART peripheral in the base platform, and we currently see the Linux kernel debug messages printed during the course of the Linux boot. So if I scroll up, what you can see is that we really boot the entire software, starting with the ARM trusted firmware, followed by the UEFI, followed by the Linux kernel version 3.17. And once the Linux is booted, I can operate the system as I would use, for instance, a VMware or any other virtual machine. So I can go and now switch to the VGA frame buffer console and, for instance, just issue some Linux commands. So let's have a look at the file system. I can also show you the underlying hardware platform as it is seen by Linux by using the proc file system. So you see it's a 8 processor platform based on ARC64. All 8 processors have been booted, and the hardware, the underlying hardware platform, is the base platform from ARM. So the interaction of the platform right now happens through the keyboard and mouse interface peripherals, and yeah, this window is exposing the frame buffer of the color LCD controller, and yes, I can operate this system as it would be a normal Linux running natively on my host. Yeah, and quickly from a debugging point of view, at any point in time I can launch and attach a debugger. Here, for instance, Lauterbach Trace32 that is attaching to the underlying virtual prototype. Here I can suspend the system. It's right now in the idle loop. I can perform any operations in the debugger that I could also perform with a typical hardware target. So here we are going to set a breakpoint, let's say in the interrupt handler of the Linux. So here we are in the interrupt handler, putting a breakpoint here, continuing the simulation, and the breakpoint is hit, and can perform now my debugging steps, whatever they are. One thing which is worth to mention, and this is different from debugging hardware, when I now suspend the system, the entire system is suspended, meaning I'm not only suspending the processor core through the JTAG, the entire underlying hardware platform is stopped, and the software cannot really tell whether it is stopped or not. We call that non-intrusive debugging. So any operation that I perform from a debugging point of view in terms of control and visibility, such as inspecting registers, is invisible to the underlying embedded software. And this non-intrusive debugging is really very beneficial, specifically when you're going to debug hardware-dependent software where you would like to suspend the system.
Now with the VDK, we also equip the software developer with additional tools which allows him to debug
beyond the processor deep into the platform, and this tool is called VP Explorer, which I would like to explain in a little bit more detail now. A hardware browser, first of all, allows the software developer to easily understand the characteristics of the underlying platform. This means which peripherals are included in the platform, at what address are they mapped, which interrupts are provided by the peripheral, how are they connected, and all those aspects can be easily determined using VP Explorer. Those kind of information you typically would need to look up in the programmer's manual of the platform. Now further on you can go and debug the different peripherals, look into the registers, their signals, add watch points, as well as traces for debugging. And all of that can be entirely scripted, so you get repeatable debug and test scenarios. And the traces then presented by VP Explorer really allow you to understand the system from a bird's eye perspective. So the processors first of all expose an OS-aware trace of the system, so which threads are launched, which interrupts are coming in, which interrupts are then handled, and how does this information correlate with the activity on the hardware, such as signal changes on the interrupt lines or modification changes in the registers of the peripherals. So this overall trace flow allows you to debug the problem from a top-down, deep into the details of the hardware.